let's start again. Okay, more people are trickling in. Come on in. Okay, this is our fourth lecture cover this time also. So hopefully it'll be fun. Does everyone have a space? Do we still have a space problem? Yeah? Okay. I'll send another email, but it seems to be tough to actually get a room at this time. We'll see how many of you drop after Lab 1 deadline. How many of you are thinking of dropping? No one? That's great, actually. That's good. There was one suggestion to hold the lecture outside. Who's in favor of that today? Wow, 3. 3 brave souls. Well, we may try that some other time, but it's really cold today, so. Okay, let's get started. Well, I guess before we start, you know that there's a lab due this Friday, right? Everybody is working on it. It's going well. It's easy. It should be relatively simple, the first one. It'll get harder progressively. Okay, this is where we left off. We were talking about complex versus simple instructions. We introduced the concept of the semantic gap, and this was the example I stopped at. Right? This was a small semantic gap in x86. Let me draw that picture again of the semantic gap. And this was an example instruction from x86 that showed that you could actually copy one string to another with just a single instruction. Remember, the semantic gap was, where do you place the ISA? High-level language, control signals. Small semantic gap means you have complex instructions. And ISA is closer to high-level language. You have a string copy instruction, for example. Repeat move S. In fact, in x86, you can do other things. This repeat prefix is a prefix to the opcode that basically says repeat this instruction until the count register becomes 0. Count register is ECX. It's actually a very powerful primitive, right? The compiler can implement loops this way much more easily with a single instruction, right? By setting up the registers. I'm not going to go over this in detail. We briefly looked at this, right? But it's a very complex instruction. It could actually, basically it starts from the source and destination pointers from each string and copies the character or byte or a word or a double word in x86 terminology. It could be a byte, it could be 2 bytes, it could be 4 bytes, it could be 8 bytes to the location pointed to by the destination register. And it does it until the ECX register becomes 0. It should be somewhere here. Yeah, count register, it goes to count register -1. If count register is 0, then exit the loop. Otherwise, keep doing this, basically, keep doing copy. And you could put a value into count register that's huge. So this instruction actually copies megabytes, maybe gigabytes of data. You could try this on your x86 computers. It's fun. Actually, you're going to do this in your homework. How many instructions does this take in ARM and MIPS? That's going to be your homework question. How many of you have done it? Not yet? You have? Okay. So you figured it out? You see it's how powerful it is, right? Compared to ARM and MIPS. It's beautiful. So one thing that I've discussed earlier is how do you actually implement this in the microarchitecture? Now in many x86 processors today actually implement this as a series of micro operations. So when they see this instruction, they don't do everything at once, but what they do is they break it down into smaller micro operations, basically very similar to the code you would write in ARM and MIPS. And there's a microcode engine that translates in hardware this instruction into those micro operations that get sent down the pipeline. So it basically gets translated into a series of adds, multiplies, loads, stores, and branches, micro branches, that are not visible to the programmer. The programmer does repeat move S. Internally, the hardware translates this repeat move S into more primitive micro operations, or AMD calls them RISC operations, I believe. ROPS, yes. This is one could call this the micro ISA. We talked about translation, the power of translation. This way you can keep the hardware simple. Hardware still executes just the primitive operations, but the software is written at much higher level. ISA is much at a higher level, and there's a translation layer over here that enables keeping the hardware simple, and that enables the benefits of a more complex ISA. And what is the benefit of a more complex ISA? Well, code size, right? Code size would be one benefit. You have just one instruction. Remember, it was just 2 bytes, right? I don't remember the opcode. I think FA was one of them, if you remember one of the earlier slides. But it was just 2 bytes to express a series of operations, maybe potentially millions of operations, right? So you can get the benefits of both worlds by having this additional translation layer between the ISA that's visible to the programmer and between a micro ISA to which the instruction gets translated. Okay, we'll get back to this again. Okay, there are other examples, and I would encourage you to read this VAX 11 780 architecture handbook. This is perhaps the most complex architecture that was ever designed. And I'll give you just some examples very quickly. Find first, we've talked about, find the first set bit in a bit field. And we talked about how it helps OS resource allocation, right? If you have a resource that has multiple instances, if all of the bits are set, that means that all of the instances of that resource is available, right? Basically, to figure out which one to allocate, you can try to find the first set bit in that bit field. This could be processes. This could be threads, for example. It could be thread contexts, right? Save context, load context, special context switching instructions that do a lot of the work for context switching. You can imagine a lot of instructions are saved if you use these instructions. We talked about operations on doubly linked list. We talked about the index instruction that motivated reduced instruction set computers, right? You can index an array with bounds checking in a multidimensional array. You could do string operations also in VAX. It had a cyclic redundancy check instruction. You can see how complex it is. I don't know if it's used, but you can see these are also specialized instructions, right? These may not be used in all programs. There was an edit PC instruction. Basically, it implemented editing functions to display fixed format output. This is interesting. Basically, you could format the output such that it gets displayed on the screen. And there were a bunch of other instructions. If you're interested in exotic instructions, it's a good handbook to look at. Okay, so basically, the point is we have small versus large semantic gap, which dictates CISC versus RISC. CISC means complex instruction set computer, and it's mainly characterized by complex instructions. And it's initially motivated by not good enough code generation. I said that also in the last lecture. At that time, in the early times of computer design, compilers were not that good. Software was not as good. It was not. They were not good at optimizing the instructions. So people decided to keep the distance between the high-level language and the ISA small, such that you didn't need to do a lot of work in the compiler. And that was the initial motivation. But over time, reduced instruction set computer got motivated, one of the motivations I described, and it's mainly characterized by simple instructions. And one of the proponents of it was John Cock at IBM, who won the Turing Award for his work in compilers, actually. And his goal was to enable better compiler control and optimization, such that the compiler can orchestrate anything that's done in hardware. Hardware doesn't do any kind of scheduling, but the compiler does all kinds of scheduling. So his idea was to have open microcode, control signals as your ISA. And this kind of thinking, you could call this crazy, right? It's crazy. All of the control signals are available to the compiler, who's going to generate all of those control signals. But this kind of thinking enabled a lot of the compiler development over time. And his work in compilers won him the Turing Award. So if you're interested, you can look him up. But there were several motivations for RISC based on the CISC architectures. One was simplifying the hardware, because people thought there were a lot of these complex instructions. Why don't we simplify the hardware to get lower cost and higher frequency? The other one I just discussed, enabling the compiler to optimize the code better. As compiler technology developed, we wanted to have better compilers to optimize the code. So the benefit of this is, one of you mentioned last time, if you have a big instruction, the compiler cannot reorder, right? It's just a single instruction, repeat move s. Whereas if you have chunks of instructions, smaller instructions, now the compiler has the ability to reorder them, right? so that you can get better performance. So if you have simpler instructions, the compiler has more control. This enables fine-grained parallelism to reduce stalls. We will see the concept of stalls in pipeline soon. Right? How many of you know of stalls? Okay. If you don't know it, that's okay. Yeah, no. But just think of, can you do optimization if you have if this is the only instruction that the compiler can produce versus the compiler can do add, multiply, load, store, I'm just making it up, and branch, and do this. Now the compiler can reorder instructions such that you still get the effect of copying one string to another, but the individual instructions can be executed in different orders. Right? The compiler has a lot more flexibility if the instructions are finer grained, if you will, or simpler. Whereas if the compiler has only repeat move s, it has no flexibility. Hardware has all the control, right? Basically, the hardware's implementation of repeat move s dictates performance. The compiler is almost out of the loop because that's the only way it can generate code. Whereas if it has these primitives, there are many, many ways it can generate code. It can reorder instructions to get better performance. That was one of the main motivations of John Koch in RISC, reduced instruction set computing. And why was this actually important? Well, because there were memory stalls. When you have a memory access in one of the large instructions, for example, when you needed to copy, when you needed to load one element from the source string and then store that to the destination string, let's say this took 100 cycles because memory is far away, memory is slow. We've discussed this, right? Well, if the hardware implementation is not that great, maybe all of the operations coming afterwards would wait, right? Because you need to wait for this data such that this store can be done, such that you can move on to the next copy in the string, right? You're copying one string to another. Basically, you're loading this element over here and storing it over here. If you get a cache miss, if this takes 100 cycles, you don't move on to the next one. You wait until you get the data such that you can copy it to the destination, and then you do the other load, and then you do the other load. If the hardware implementation is not good, it may take a long time to actually execute this entire string copy. Whereas if the compiler can reorder the code, what it can do is it can hide some of these stalls, right? It can first do load of this element into some register, let's say register 1, and then it can do load of this element into register 2, and then load of this element into register 3, and then load of this element into register 4, dot, 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 dot. Right. So instead of having one load and then waiting for it, it can enable the processing of all of those loads in parallel. Right. We'll see this concept later on. I just want to give you the idea for now. But you really do not need to wait for the result of this load to initiate the next load, because these are really independent. Right. The only time you need to wait is when you really need to use this register 1. Right. And when does that happen? When you actually need to store this value that's loaded into the destination. So now the compiler can reorder the code such that it can do a bunch of loads first, and then a bunch of stores next. That way, even if a single load takes 100 cycles, you're doing multiple loads in parallel, assuming you have enough ports to memory. And you can enable much better performance. Does that make sense? So you'll see a lot of these concepts coming together later on toward the course, but this was the initial motivation for RISC. And that's a great motivation, right? Because now the compiler has a lot of control. It can enable much better performance. Now it turns out you could actually do this in hardware as well. And we'll take a look at that, right? You could actually, you don't need to have an implementation that just does one load and then waits for 100 cycles and then does the store, and then does the other load, waits for 100 cycles, and then store. The hardware can itself reorder these instructions such that it gets a schedule that looks like this. And that's called out-of-order execution. And we'll see that later in the course. Okay? Okay. So how high or how low can you go? We've discussed very large semantic gap, which is compiler generating control signals. And I guess I've talked about all of these, so I don't want to go over this again. This makes the compiler a lot harder to design, obviously, right? Because now the compiler needs to generate the complete set of control signals for every single operation, every single instruction. It needs to know the machine really well. The other downside is it ties the compiler very closely to the implementation, right? Anytime you change the implementation, anytime you want to add another control signal, well, you need to change the compiler, right? You need to change the program. In fact, backward compatibility becomes a little bit difficult with this one, right? Because you need to maintain all the control signals that you previously maintained, plus the new control signals you add should not affect the old programs that were written for the previous control signals, right? That's going to be very tough. So there are downsides to this crazy idea, but that crazy idea gave way to a lot of good research and good ideas that became reality later on. So very small semantic gap. You could go the other way also. You could make the ISA the same as high-level language. And people have tried this as well. People have tried to build Java machines that can directly execute Java code, Lisp machines, Prolog machines, actually. These are languages. Have you ever used Lisp or Prolog? Some of you have. That's good. They're fun to use, right? Maybe. These are languages that are easy for some programmers, and people have looked at developing those machines such that the compiler doesn't do a lot of work compiling those languages. Object-oriented machines and capability-based machines, which we briefly discussed early on. Okay, so basically you can make the high-level language the same as your ISA. So ISAs have actually there was a question. Yeah. Okay. So ISAs have actually evolved also. This is kind of an evolution of computer architecture in the 60s, 70s, or maybe 80s or so as well. ISAs have evolved to reflect and satisfy the concerns of the day, just like everything else, right? We've talked about architecture as an evolving thing, a Hammerschlag hole evolving from a boiler room, right? ISAs have evolved also. Why did we have CISC initially? Well, it was not only because of the compiler technology, but also on-chip and off-chip memory size was very, very limited. And one of the big advantages of CISC, complex instructions, is code density is very, very high, right? So you really would like that. Well, we talked about this. Limited memory bandwidth, that was true early on. That's going to become even more true going forward. We're putting more cores on chip today, and where the pin count out of the chip is not scaling very well. We cannot increase the number of pins. So going forward, some of the characteristics of the CISC ISAs might be very useful. And over time, we'll cover this later on in the course, but need for specialization in important applications drove changes in the ISA also. For example, x86 ISA added the MMX extensions, multimedia extensions, which are now, I believe, SSEX or maybe something else. Have they changed the name again? There was SSE4 at some point. Streaming SIMD extensions, streaming single instruction multiple data extensions. But these are basically enable processing for multimedia applications. And we'll see that these are a small scale form of single instruction multiple data operation. Basically, you have an instruction that operates on multiple data elements. Let's say you're adding two arrays together. You can do that with a single instruction. That's the idea. And there are many other features that were added to ISA to enable important applications. For example, virtualization is one example. If you look at many ISAs today, there are virtualization extensions, right, to support virtual machines better. And that reflects, again, concerns of the day, because virtualization is important today. One of the nice things about ISA evolution is the use of translation that we've discussed, both in hardware and software, has enabled the underlying implementations of the hardware to be simple and similar, in fact, regardless of the ISA. Some people have said that ISA doesn't matter for this reason. Well, that's very microarchitecture-oriented view, if you will. For a microarchitect, ISA doesn't matter because you can always use this translation layer and implement the same thing underneath, right? Basically, ISA is the hardware-software interface, and there's a translation layer, but then there's another interface over here between translation and interpretation. Interpretation is really where you execute the instructions. Here, you're doing translating from a set of instructions to another set of instructions. So this kind of indirection, this layer of indirection enabled the hardware to stay simple. Now let's take a look at that translation layer a little bit more. Basically, one can translate from one ISA to another ISA to change the semantic gap trade-offs. Right? We talked about existing, well, this could be actually any arbitrary ISA as well. People have tried to translate from x86 to PowerPC to x86. In fact, the virtual machines you're using are doing this. They're translating from one ISA to another ISA. But I'll give you some examples from the x86. Basically, Intel's and AMD's x86 implementations translate x86 instructions such that they can execute instructions that are written in x86, programs that are written in 86, into programmable invisible micro-operations or micro-instructions, simple instructions, RISC operations in hardware. This translation layer is in hardware. Make sense? And we'll see examples of this later on. And you could do this in multiple ways. What you could do is, I'll give you one example, actually. This is very similar to how repeat MOVs is implemented in existing x86 architectures. Let's say you got the repeat MOVs opcode. I don't remember what it was, F0, CA. Somebody can check if they if they have the previous set of slides. Let's say you've decoded this, right? You've decoded and you found that this is a repeat MOVs. Basically, the processor goes into a special mode. It's called the microcode engine mode. It's unfortunate, but it's very similar to microcoding, as we will see. Basically, it indexes into a memory array that contains a set of instructions that would implement repeat MOVs, set of micro-instructions. And the processor will start a micro-program counter. And the first thing could be basically checking whether ECX is 0, right? Because if ECX is 0, then you don't need to do the string copy. ECX is the count register, remember? This determines how many bytes or words or data types of different quantities that are specified by the instruction that you need to copy. Basically, you have these instructions: add, multiply, store, load, microbranch, that are stored in this microcode read-only memory, microcode ROM. And the processor goes into a special mode where it cycles through this microcode ROM. And it issues micro-instructions into the pipeline, and these micro-instructions get executed. That's how the translation is done. You take this opcode and you translate it into smaller micro-instructions. There are other ways to do it, actually. This is one way of doing it. Here you have a microprogram counter and you need to increment it. But there are other ways in which you can actually take the opcode and decode it. And actually, in hardware, you can have some combinational logic that generates micro-instruction 1 and then micro-instruction 2, let's say. Let's say this. Let's say you're doing what could be a good instruction. One example is increment a memory location, right? Memory location specified by R2, let's say. Actually, in x86, it's easier to write it. Increment something like this, EAX, basically memory location specified by EAX. In x86, in one implementation of x86, this could be translated to load memory location into a temporary register, and then add, actually x86 contains an increment instruction, increment temp, and then store this temp back into the memory location that's specified by the EAX. Now this could have 3 micro operations, right? So I'll add one more micro instruction too. So when the processor fetches this instruction, when it decodes it, it has this combinational logic that generates 3 micro instructions. And this gets sent down into the processor pipeline. That's how you can do the translation. You might actually do some of this in your implementations later on in ARM. Actually, if we change the architecture to x86, you'll have fun doing all of this. But now you can imagine two different styles of translation in hardware. One is microcoded. You store the instructions, and the other is more combinational logic. This is done in existing processors for instructions that require no more than 3 or 4 micro-instructions because it's easier to do. But this is done for instructions that require more than 3 or 4 micro-instructions. Right? Remember, the repeat MOVS can require millions and millions of micro-instructions. Right? That's why this is a powerful translation mechanism. Okay. Any questions? Am I going too fast? Too slow? Okay. No comments, because people are still freezing. Okay. The other approach, well, this is also translation, but Transmeta, this is another example. Transmeta's x86 implementations translated x86 instructions into secret VLIW instructions. Actually, these are secret too. The micro operations that we have in x86, Intel's and AMD, its implementations are also secret. But Transmeta translated the same x86 code into secret VLIW instructions in software. Basically, this translation layer was purely in software. And they did a lot of optimization of the code. And if you're interested in this, there's a nice white paper by Alex Kleiber. It's called The Technology Behind the Transmeta Crusoe Processors. It's a little bit high level, but it's a good read. I think you can still find it on the web. If not, we can put it up on the web. It was written in 2000. It describes how this code morphing software works. Of course, not the details, but how overall. But you can imagine a similar thing, right? The code morphing software can do this. But what they additionally did was, with this code morphing software, because this is software, they collected a lot of information about blocks of code, which pieces of code were executed a lot. And they try to optimize that code. It's very similar to a lot of the dynamic compilation engines that we have today. You can have code. Java, for example, works this way. In Java, the programs, at least the Java virtual machine, works this way. The programs that are written over time, as they execute, the virtual machine figures out what are the hot code blocks, what are the code blocks that are executed very, very frequently. And the virtual machine recompiles the code dynamically such that it tries to optimize the code based on the data values that it's seen. It tries to optimize those hot paths. And we'll see some of those optimizations when we talk about static instruction scheduling. I don't remember what lecture number it will be, but probably around 20 or so. Okay? So this translation layer could be very powerful. I think you can think about the trade-offs. Any questions? Okay, let's move on. Another ISA level trade-off that's related to CISC versus RISC is instruction length. How long should the instructions be? We've talked about the complexity of the instructions. What about the length of the instructions? Well, if you have fixed length of all instructions is the same. Variable length, exactly the opposite. Right? Length of instructions is different, and that's determined by the opcode and sub-opcode, and many other things potentially. Well, there are upsides and downsides to both, right? What is the upside of fixed length? Anyone? Yes? Simple decoding, yes. What else? If there's any, yes. Alignment. It's easier to fetch, that's right. I think it's all easier to decode also once you align things. So basically, simpler decoding in general. Easier to decode single instruction hardware. It's easier to decode multiple instructions concurrently. Well, we're going to talk about decoding multiple instructions concurrently. But this is one way of enhancing performance. This is called superscalar processing. Basically, the idea of fetching and decoding and executing multiple instructions in parallel. And if your instructions are fixed length, you know the boundaries of the instructions, you can very easily have decoders working on the different instructions in parallel totally independently, right? Because you know where your instructions are. You know how long they are. I'll erase this. Whereas if you have variable length instructions, now you have difficulty in decoding both single and multiple instructions, right? Let's say you have a decoder 0 here. Now if you want to decode the second instruction, let's say you fetched a bunch of bytes. This is a bunch of bytes, I'll call it. And this is also a bunch of bytes. If you have fixed length instructions, you know where the instructions are, right? Easily. And you can ensure that this decoder works on this instruction, this decoder works on this instruction. If you have the same bunch of bytes, but if you have variable length instructions, you don't know where this decoder should start working on until this decoder finishes, right? At least until this decoder figures out how long this instruction is. Because it's variable length. This instruction could be 1 byte. This instruction could be, I don't know, maybe 8 bytes. So this decoder should start looking at this byte or should start looking at this byte. So there's a dependence in the decoders, right? Because the previous decoder needs to know where the previous instruction ends. And the next decoder needs to know where the previous instruction ends. So you cannot decode multiple instructions completely in parallel. Does that make sense? Actually, even a single instruction completely in parallel you cannot decode. We'll take a look at that. Okay, what is the downside of fixed length? Well, if you have fixed length, you're now wasting bits in instructions because you may actually not need a field in an instruction, but you still need to have the same length, right? And we'll see examples of that. And it's also harder to extend the ISA. If you have variable length instructions, you can keep adding larger and larger instructions, right? Whereas if you have fixed length instructions, it becomes difficult to do. So people reserve opcodes for this reason. Actually, in a variable length ISA, it may still be a good idea to reserve opcodes because there may be an important instruction that's going to be used a lot that you want to add later on. Okay, variable length upside is compact encoding. Basically, it's the upside we've seen in any variable length encoding mechanism. Right? This is obvious, right? Okay. Why is this good? Like, why do you want compact encoding? What benefit does it provide? Any thoughts?
Compact code.
That's right, yes. Your code is small. Yes, what else?
So that means loaded faster.
That's right. You don't need to go to, you say memory bandwidth, right? And you can utilize your caches more efficiently later on when we get to the course. So you could go to the extremes. Intel x86 actually has variable length instructions, and we'll see that. But Intel 432 had Huffman encoding of instructions. Do you guys know Huffman? You do? Okay, I'll let you study that. But basically, an instruction could be 6 bits, or an instruction could be 321 bits. And the idea was to minimize the expected size of the instruction. That's how they encoded the instructions. So what they did was they profiled all of the programs they had, and they figured out which instructions were most commonly used. They figured out the frequency of each instruction. And based on that frequency, they assigned a code to the instruction. For example, an instruction that occurred 55% of the time got the smallest code, because you would use that instruction more frequently, so you want to have a smaller code for that. Its encoding was smaller. That's the idea behind Huffman encoding. You figure out how often each code word occurs, and you assign a code to each code word such that you minimize the expected length of the code words. Expecting the length of the codes for all code words. So for example, add instruction had 6 bits. An instruction that was very, very infrequently used was encoded in 321 bits. And I don't know why it's 321. But that was the idea. So you could go to the extremes like this. So you can imagine that this is a lot more difficult to decode, right? Now you need to figure out where the opcode is in each. And we'll take a look at it. So the downside of variable length, this is a big upside. It's compact encoding. It can benefit performance in many different ways, right? It can improve your cache utilization. It can improve your memory bandwidth. It can improve, you don't need to use as much memory. The downside is you need more logic to decode a single instruction. And it's harder to decode multiple instructions concurrently for the reason I explained over here, because you do not know the length of the previous instruction. Okay. There are trade-offs associated with it. We talked about code size, memory space, bandwidth, latency versus hardware complexity. Right. Here, code size is nice, but hardware complexity is higher. ISA extensibility and expressiveness. ISA is easier to extend, and it's probably more expressive over here. You can add many, many instructions. Downside is, again, hardware complexity. Performance is interesting over here. You have smaller code here. As a result, you have benefits in terms of memory space, bandwidth, and latency. But ease of decode can reduce your performance, right? Because it's a lot harder to decode this one. And you can have a more complex decoder. Now, it turns out if you design your decoder well, the performance of this should really be higher in general. Because decoder should really not be on the critical path. And memory is a lot more important in terms of performance, all of these things that we have discussed. I guess there's one other trade-off over here, which is energy, right? What do you think? Do you think variable length is better for energy or fixed length is better for energy consumption, which would consume less energy for the same program, same work done? Fixed length? Yes, there's. There you go. Now you're coming to the trade-offs. One of you says fixed length because it has less logic for decoding, which is true. And you say variable length because DRAM uses a lot more power, and with compact encoding, you're accessing DRAM less frequently. These are both correct, actually. It's not clear which one would do better. It really depends in this case, because you're saving energy because you're not going to memory as often. You're not using as much memory. Whereas you're losing energy with variable length also at the same time because decoding is a lot harder. Right? Your decoder is a big piece of your die area. In fact, if you look at an x86 chip today, the decoder is huge. A lot of x86 chips today decode 4 instructions per cycle, I believe. It used to be 3, but they've increased it to 4. But that decoder is huge. Exactly for the reason I say over here, because you can have a full decoder here, but how do you decode multiple instructions per cycle? Right. So they use a lot of tricks to try to decode multiple instructions, and we'll hopefully get to it when we talk about superscalar processing. But I'd like you to think about how you would design a decoder that can decode multiple instructions per cycle when you have variable length instructions. Okay. Actually, this is similar to if you guys have looked at compression at all. There are compression algorithms that you must have used by now. bzip, for example, gzip. Have you guys used that? Or compress? They do variable length compression. And decompression has the same issue, basically. You need to know the previous. You need to figure out you need to decompress the previous portion to figure out to decompress the next portion. Not all compression algorithms are that way. Some compression algorithms are actually fixed length, if you will. But they and again they have the same trade-off basically. If you have fixed length compression algorithm, then your algorithm wastes space. Whereas if you have variable length compression algorithm, your algorithm packs things much better, but decoding complexity, decompression complexity increases. Okay, another ISA level trade-off, uniform decode. Have you guys heard of this before? Well, we've talked about it, right, in the last lecture, so I'm going to go over this very quickly. Uniform decode means same bits in each instruction correspond to the same meaning. Opcode is always at the same place. Well, not always, but mostly at the same place, let's say, because we can have instruction groups also. Operand specifiers, similarly, immediate values are always at the same place. Many RISC ISAs follow this, alpha, MIPS, Spark. Non-uniform decode, exactly the opposite. For example, in x86, opcode can be the first, can be anywhere between first or seventh bytes. Right. We need to figure out where the opcode is. That's the first thing the decoder needs to do. The upside of uniform decode is obvious. It's easier to decode, right? It's simpler hardware. It enables parallelism also, because you know where something is. You can start doing things speculatively. Speculative means the hardware can start operating on an instruction before it knows what that instruction even is. For example, if you know where the immediate value offset of a branch is, you can generate the target address of the branch before even knowing that instruction is a branch. Right? How can you do that? Let me see if I have it over here. Well, I guess I do have it over here, yes. This is what alpha looks like. Opcode is always here. And this is the branch format. If you look at this, you know that the displacement value is always here. And alpha calculated branches as, I believe, PC relative branches. You could have PC relative branches. You could take the program counter and you could add the displacement to it speculatively, without even knowing that the branch is a branch, right? The instruction is a branch. That way, you generate the target address by the time. At the same time, you know that the instruction is a branch. Now, this could be useful, right? This could be useful because you may need that next program counter from the branch to feed into the change the program counter in the next cycle. Right? If you have this kind of uniform decode, you can do things speculatively, and we will see why this is useful when we talk about branch prediction. But keep this in mind for now. You can actually do a lot of different things, assuming that the instruction is something. Okay. So the downside of this is now it restricts instruction format, right? Or waste space. So if opcode always has to be here, now your instruction format is restricted. Right? It's not like non-uniform decode. Non-uniform decode, the upsides we've discussed earlier a little bit. It has more compact and powerful instruction format. Right? You can have anything, any field, anywhere. The downside is more complex decode logic. And non-uniform decode normally goes with variable length also, but it doesn't have to. So let's take a look at these two instruction formats. Again, this x86 over here, alpha over here. You can see how regular this is, right? Opcode, register A, register B, register C, always here. This is the branch format, this is the memory format, this is the operate format. And, well, I guess we'll get to MIPS. I'll cover a lot on MIPS today, and I'll let you figure out ARM a lot. But let me cover x86 first. If you look at x86, this is a variable length ISA. The smallest you can have is 1 byte opcode. That's it. You can have a 1 byte opcode instruction. And it could be very powerful. It could specify, for example, increment this register. Or I believe increment this memory location specified by this register can be expressed in 1 byte also. As I said, repeat and west can be expressed in 2 bytes. But you could actually have prefixes. And you can have up to 4 prefixes before you get to the opcode in the instruction. What are some of these prefixes? Repeat is a prefix. Repeat means do this instruction until ECX becomes 0. Lock is a prefix. Do this instruction atomically. Ensure that no other instruction gets in the way. You can read the manual for more exact specification. And you can have up to 4 bytes of those. And then you could have 1, 2, or 3 byte opcodes. And these are the addressing modes which we will cover. And some of these are required. These are optional, as you can see. These are optional depending on the opcode. These are optional also depending on the opcode. Again, it could be 1 to 4 bytes. These are optional depending on the immediate values. They're also optional depending on the opcode. It could be 1 to 4 bytes. So if you add all of these, I think an x86 instruction could be 15 bytes, anywhere between, or maybe 16 bytes, 1 to 16 bytes. That may have changed. I haven't kept up with the x86 latest version of the x86 ISA. So you can always extend the ISA, right? So these determine how the addressing mode is calculated, and these this is for the displacement. I mean, we'll see this soon, how you get part of the address. And this is an immediate value. MIPS instruction format is actually similar to alpha. It's simple. It's clean. And I'll cover this a little bit. But there are three types of instructions. This is R type. It has 3 register operands. This is operate instructions. And this is the I type. This basically has 2 register operands and a 16-bit immediate operand. You can see that the opcode is here. These are actually opcodes. 0 means it's really an opcode, right? Function is a sub-opcode. RS, this is the source register. RT is either the destination register or the other source register. RD is the destination register. And this is the J-type operation. It's a jump instruction. Basically, it just has an opcode and a 26-bit immediate operand, where you can get the destination value. So you can see that this is also simple, right? It's simple decoding. You have 4 bytes per instruction, regardless of the format. It must be 4-byte aligned. Basically, 2 least significant bits of the program counter must be 0, 0. And format and fields are easy to extract in hardware. And multiple instructions are easy to decode. Whereas you can see that multiple instructions would be horrible to decode with x86. Right? OK. And this is what you need to deal with, at least partially. ARM. We're not requiring all of the formats. But ARM is actually not fully. You can see that it's uniform decode, right? Mostly, at least. Well, mostly. But it's not as simple and clean as the dead alpha and not so popular MIPS. But I guess it's working for ARM. OK, I'm not going to cover this, but one thing that I'll briefly mention is condition flags are over here. This determines under what conditions the instruction should be executed. This is the notion of conditional execution or predicated execution in ARM. Every instruction is conditionally executed. And that condition is specified by the top 4 bits. Okay, you'll get to know that really well. Okay, uniform decode usually yes.
Back on the last slide, what are those
Sure.
numbers at the top and bottom mean?
Did somebody ask this in last lecture?
Yeah.
Yeah.
0 to 31.
Okay, yeah. So it's actually, I don't know why they did it this way, but basically it's 0 through 31. It's the bit number. I don't know if we had it over here. We didn't have it over here. Yeah, it's like this basically. It's the same thing. It's a bit number, 0 through 31, but it's written vertically rather than horizontally. Yeah. Yeah, that's the interesting thing about human mind, right? That's the exact same question I asked also when I first saw this. I don't think vertically. I think horizontally. And what is this? OK, uniform decode usually goes with fixed length. It doesn't have to, I guess, but it usually does. Because it's more of a choice of philosophy. Yes?
Oh, I was going to ask a curiosity question.
Yeah.
In the ISA specs, like in general, is there normally a difference between like reserved and then undefined? Because I'm just thinking if there's ever a case like where an instruction format was made undefined and then later made into an instruction that causes the ISA.
Actually, that's a good question. I don't know if there's a reason for the difference in the terminology. I've never thought of it. My feeling is there is no difference. Reserved means if you use it. So the ISA, usually the ISA manual defines what happens. So if something is undefined, they say you'll get unpredictable behavior. Don't count us on anything. I assume there's something similar with the reserved, but I haven't read it in any ISA manual.
I was just wondering if there was like a general trend. Because I know for ARM, like there's a distinction between, it does just wondering if general.
So in ARM, there's a distinction between reserved and?
I think, because like for reserved,
Uh-huh.
I could be wrong on this, but I like for undefined, it will go to an exception, right? Well, then reserved possibly do anything.
OK, I see.
Like for an undefined exception, it will go to one exception.
I see.
So I was just wondering, like, if there's like ever an issue with that.
So that should be specified in the ISA manual. That should be clearly specified. But I don't think there's a general definition in computer architecture of the distinction between reserved and undefined. Yes?
Well, yeah, on the ARM processor, the undefined is it's used to like communicate to coprocessors.
Oh, okay.
So when you and then you can overwrite the exception handler and you can use that. You can make like a little an exception routine that actually communicates to a coprocessor. But the undefined instruction is like for extensions later.
Okay, I see.
Reserved instruction. Sorry.
Okay, it's I see. So the ISA clearly specifies this, right? They have to, yes. Mm-hmm. Yeah, but I don't think there's a general distinction between those two. Okay, so in a variable length ISA, uniform decode can be a property of instructions of the same length. Basically, uniform decode, if you have instructions of different lengths, it's very hard to think of uniform decode, right? Because instructions are different lengths to begin with. Okay, usually these are different philosophies, right? RISC is intended to give more power to the compiler and less complexity to the hardware. CISC is intended to basically do a lot more on the hardware side to have complex instructions and also get other benefits. But the RISC philosophy consists of simple instructions, fixed length, uniform decode, and few addressing modes. Whereas CISC philosophy, complex instructions, variable length, non-uniform decode, and many addressing modes. So if there's one definition of RISC versus CISC, this is probably a good thing to look at, good thing to think of. Okay, let's go to a few other ISA level trade-offs. Well, we're going slowly. I was hoping to cover all of the slides today, but we'll see. Number of registers is an important trade-off. Again, this affects number of bits used for encoding register address and number of values kept in fast storage. Right? Basically, how large your register file is. Right? And this definitely affects your performance, as we will see over here. This affects the size, access time, and power consumption of the register file. Right? If you have 1,024 registers, then you have a large register file, and you have to build it, because that's specified by the ISA. Right? Although one could, it's a good exercise to think about how do you circumvent building a huge register file, even if your ISA specifies it, right? Well, you could really have a small register file in the microarchitecture and keep loading it from memory, right? Some other space that you manage. So you don't have to obey exactly what the ISA does, as long as you give the illusion to the programmer that you're obeying what the ISA does, right? Okay. So large number of registers, I'll go over this. I guess I'll ask you the next one. Large number of registers, the upside is that it enables better register allocation by the compiler, right? Remember, the registers are there for a purpose. The values that are used frequently, the values that you keep accessing, are kept in this fast storage. And if you have a larger number of registers, then the compiler has more flexibility in allocating more values into that. If you don't have enough registers, then the compiler needs to, if operations are done on a value, the compiler needs to keep that value. But it doesn't have enough registers, so what it needs to do is it needs to save some value to memory for a while and then restore it back. This is called spilling into memory. And we may cover that at some point later again. But basically, let's say you have only 8 general purpose registers, which x86 used to have until recently. But the compiler needs really 9 values that are alive. Alive means that are being used right now and also that need to be used for the computation. Well, this is too bad, right? The compiler cannot keep everything in those 8 general purpose registers. So what the compiler does is it keeps 8 of them here, and the 9th value it keeps in memory. And when the value is needed, it loads it from memory, from the stack. Basically, it first needs to save one of the 8 onto the stack. This is called a spill. Basically, store onto the stack one of the values, and then load this 9th value from the stack. This is called a fill. But then the compiler will need this value that was saved on the stack. So it will need to basically store some other value onto stack, spill it onto the stack, and then load this value that it saved earlier and fill it. So basically, what I'm getting at is the register file will be thrashing, right? The compiler needs to manage this register file with these spills and fills, stores and loads into the stack such that this value, when it's needed, gets into the register file, but some other value from the register file needs to be saved onto the stack such that you keep the value somewhere. Right? So this is bad. This is basically, this is called also thrashing. You do not have enough space in your register file, I'll call it the register file thrashing, to hold all of the values that are needed by the program at that point in time. And this is definitely dictated by the number of registers in your ISA. If you have more registers, you have fewer saves and restores, and you have better performance. And this is exactly the reason x86 ISA moved from 8 general-purpose registers, which was not enough for many programs, to 16 general-purpose registers today, which is much better. A lot of RISC ISAs have 32 general-purpose registers. Well, the downside of large number of registers is obviously larger instruction size, because you need more bits to specify the register, and larger register file size. Okay. Addressing modes, I'll discuss this a little bit, and then we'll take a break. I promise that I will discuss this. This is definitely an interesting topic. Basically, addressing mode specifies how to obtain an operand of an instruction. We talked about register addressing mode, immediate addressing mode. Basically, this is the values in the register, the values in the immediate location in the instruction. And there are many memory addressing modes. And we've discussed some of the addressing modes, so I'll go over this relatively quickly. If you have more modes, well, I guess I'll ask you, what is the advantage of having more modes? You could, yes? That's right. You could potentially express high-level computations much more easily, such that you have more compact encoding. Right? Yes?
Compiler flexibility? The compiler doesn't have to, make different instructions just to move things from memory. Like do the whole loading and storing if I can access, have one register, one memory.
That's right. That's right. Basically, compiler can again map the high-level way of getting the address much more easily into the hardware. Right. Basically, I think both of what you said gets into this. You can help better support programming constructs, arrays and pointer-based accesses. The downside, as we've discussed earlier, is now this makes it harder for the architect to design. Basically, you need to support many different modes. So memory, actually, you don't need a whole lot of modes other than base plus offset, let's say. You just basically load from the space register. Maybe not even an offset, right? Memory addressing mode could be just load from the address as specified in this register. That's it. But we'll see, we've seen that there are many, many addressing modes. Displacement, register indirect, indexed, absolute, memory indirect. Memory indirect means load the address from this register, treat that as an address, and go and load from memory again. Right? So it's basically, let me specify this. Actually, maybe the next slide has it. No, next slide doesn't have it. So you don't really need that addressing mode, right? If you have memory, if you have register indirect, the value in R2 is treated as an address, and that is loaded into some register destination, let's say. Whereas memory indirect, this could be specified in an instruction, is basically this. Right? You get the address in a register, go to memory, access the data in memory at that address, treat that as an address, go to memory again at that address, and get the data at that address. Right? One addressing mode can specify this. If you don't have this, well, this is a pointer-based access, right? You're basically chasing pointers. You could actually have memory, memory, memory as well, right? If you're chasing a lot of pointers. But if you didn't have this support in the ISA, you basically need to do 2 register indirects, right? You need to load this location into memory, and then do another memRD to get the same effect. So you have more instructions to get the work done if you didn't have this addressing mode. Does that make sense? So that's the upside of more modes. Well, I guess I didn't have a comprehensive list over here, but you get better code density as well with more modes. The downside, it makes it harder for the architect to design, and perhaps it gives too many choices for the compiler. Right? That could be a double-edged sword for the compiler. If the compiler can do things in many different ways, which one should it choose? There needs to be really good guidelines for the compiler. And this is actually a good paper if you're interested in reading it. It's a high-level overview paper about how compilers and computer architecture interacts. We talked about a lot of things related to compilers and computer architecture in this lecture and previous lectures, and I would recommend this paper, which talks about how you should design an ISA such that it's easier for the compiler writer to compile into. Okay. So addressing modes. Let's take a look at some of the addressing modes. I'll give you some examples. I'm not going to cover everything. You're going to implement some addressing modes in your labs. But x86, the opcode and prefixes specify which addressing modes are used. And you could use actually all of these in the back, mod RM bytes, mod register memory, scale index base. These are all addressing mode related bytes. Displacement basically tells the address displacement. But there's a complex way of determining what addressing mode is used. And this is what it is. I guess I don't want to go over all of this, but I'll just cover some of this. This is actually from x86 manual. But you can have register index addressing mode. Your effective address is the location in the register. You could have absolute addressing mode. And this is determined based on the value in the mod RM bytes, basically, mod RM byte. And mod RM is divided into, don't ask me why they're called these things, but it's divided into these bit fields, if you will, mod, register, opcode, RM. And if the value of mod is 00, RM is 000, then the address, effective address is EAX. Does that make sense? And you could have an absolute address also. If the mod RM byte is 00101, then your address is absolute, which is displacement 32. And then you need to go to footnote 2 to figure out whatever that is. Right? Denotes a 32-bit displacement that follows the mod RM byte, and that is added to the index. Well, you need to figure out more to read that. I don't remember it at this point. But basically, you can have register plus displacement mode. Basically, this is the register. If your mod RM byte is 10000, this is your register, and this is the displacement. And you could directly specify a register also. If your mod RM byte is 11000 and the other one doesn't matter over here, you directly get the value from a register. Right? And there's this other thing over here. If your mod RM byte is 01000, then this means that you have an SIB byte following the mod RM byte. This is the only case when you have this additional mode over here, scale index base. I can ask, why am I telling you all of this? I'll get to the reason at the end. There's a much more interesting part of the x86 manual that talks about how these matter, actually. But what is SIB? Well, you see the complexity of the decoding also, right? You need to figure out what mod RM byte is to figure out whether an SIB byte actually follows it. And to figure out whether mod RM byte even exists, you need to decode the opcode first. And to figure out where the opcode is, you need to decode the instruction prefixes. So it's a very serial decoding process to get to figure out where the SIB byte is. So what is SIB? SIB is actually a very powerful addressing mode. You basically have an indexed base plus index. You can have two registers to form an address. You can have one register and a scaled index. Can anybody think of why this is a good, useful mode? Array accesses. Okay, so this could be the base of your array, for example, right? Yes. So let me give you the bigger picture. I've simplified things a little bit over here, but this is how the SIB addressing mode works in x86. You basically have a base, and you can have an index, and you can scale that index with 1, 2, 4, 8. It can basically enable you to index to a data structure that has elements of 1, 2, 4, or 8 bytes. And then you can have a displacement over here. And you can have an 8-bit, 16-bit, 32-bit, or not, no displacement. So what is the upside of this? Basically, I'll let you read some of this, but let's see. Yeah, let's do this one. You could actually use base plus displacement to address an array also in x86. You have a base register, and displacement can be used together for two distinct purposes. One, as an index into an array when the element size is not 2, 4, or 8 bytes. The displacement component encodes a static offset to the beginning of the array. This is the beginning of the array address. It's a static array. The base register holds the results of a calculation to determine the offset to a specific element to the array. That's one way of doing it. This is just one way. Or to access a field of record. The base register holds the address of the beginning of the record. You have a struct, let's say. And while the displacement is a static offset to the field. Right. Does that make sense? Okay. Now you could make it more complicated. Index times scale plus displacement. This address mode offers an efficient way to index into a static array when the element size is 2, 4, or 8 bytes. The displacement locates the beginning of the array. The index register holds a subscript of the desired array element. And the processor automatically converts the subscript into an index by applying the scaling factor. Scaling factor is how large are the elements in your array. Right? So if your array elements are 1, 2, 4, 8 bytes, you can calculate the address of the element that you're trying to access in one shot within the instruction. Right? No more additional instructions to calculate the address. This addressing mode saves a lot of instructions to calculate the address. Now you can look at this. Using two registers together, base plus index, supports either a two-dimensional array, the displacement holds the address of the beginning of the array, or one of several instances of an array of records. And you can think about this. And this is the most complicated one, which enables you to access arrays where the elements are 2, 4, or 8 bytes in size. So you can see the power of this, right? Okay, this doesn't do bounce checking like VAX does, so it's not as complicated, but it's powerful. Actually, this could have been your assignment, but the alternative, we could have asked you actually to do this address calculation in ARM, for example, or MIPS. You would see that it would take many more instructions to do the same address calculation. It takes one instruction in x86. Okay. There are other example ISA level trade-offs which I'm not going to cover. Actually, let's stop here and take a break quickly. Let's take a 5-minute break, and then we'll continue. 5 minutes is good, right? Okay. Somebody said it's 30 in here? I hope not.
I said it's cold in this entire city.
Oh, in the entire city. That's true, yes. Well, like 6 degrees in the morning, I think. That's okay. So there are a bunch of other ISA level trade-offs that we will see over time, perhaps, and some of them we may not see. But for example, condition codes or not. That's an ISA level trade-off. So you'll see that ARM has condition codes, right? Whereas some other ISAs don't have condition codes. Alpha doesn't have condition codes. x86 has condition registers, eFlags register, which is a condition code. Do you have that or do you not have that? This is kind of a side effect of an instruction, right? You don't normally specify condition codes in an instruction. In x86, for example, it's a side effect. It sets the condition code. May not always be a good thing. There are special instructions that do not set the condition codes also. You can change the opcodes such that they do not. But this is an ISA level decision. An instruction, does it specify a single operation, if you will, or multiple independent operations? Is it a VLIW ISA or a single instruction ISA? That's a very high level trade-off also. There are precise versus imprecise exceptions. We briefly talked about that when we talked about data flow, right? How do you know which instructions have executed and which instructions have not? Precise means when you get an exception or you get an interrupt, basically you have a determined precise state. No instructions that are previous to this have executed. Well, no instructions that are after this have executed. And all instructions that are previous to this one have completed totally. Right? That's very precise. This helps debugging a lot, and we'll get to that later on when we cover pipelining. Do you have virtual memory or not? Do you have unaligned access or not? We'll briefly cover this soon. Do you have hardware interlocks, meaning the hardware can enable the execution of dependent instructions correctly, or does the software needs to guarantee interlocking? Interlocking is dependency checking. We'll cover this when we talk about dependencies. But initial MIPS architectures, for example, wanted to have nothing to do with hardware. That's the RISC philosophy, right? Basically, the hardware doesn't guarantee anything. It's very simple. It's the job of the software to ensure that dependencies are obeyed between instructions, especially if you're processing multiple instructions in parallel. In fact, maybe a good homework assignment for next. Let me ask, what does MIPS stand for? MIPS, the processor ISA that we've discussed. Yes. That's a different MIPS. That's good. That's good. That's true. That's what MIPS stand for, but that's a different MIPS. That's the performance metric. What about the ISA? Maybe they did have that in mind also. They wanted to achieve 1 million instructions per second, but they had a low bar then. Because you know that we're way beyond 1 million instructions per second today, right? Nobody can guess what it is? Okay, that's your assignment for next time. Figure out what MIPS actually stood for. It's related to this interlocking. In fact, that I over there is interlocking. Okay, software versus hardware managed page fault handling. We'll cover virtual memory. Who does that? When a page is not present in physical memory, who handles that? Is it the software or is it the hardware? I say specify that. Cache coherence. Is it the job of the hardware or is it the job of the software? We'll cover that also. So we'll see a lot of these concepts. Let me get back to programmer versus microarchitect. All of these are actually related to that. Many ISA features are designed to aid programmers but complicate the hardware designer's job. This is true for pretty much everything because it's you're right at the interface, right? Virtual memory is one example. Very briefly, virtual memory frees the programmer from thinking and managing whether you have enough memory or not. That's it, right? Should the programmer be concerned about the size of code blocks fitting in physical memory? If your answer is yes, then you don't want virtual memory. And in earlier computers, the answer was yes, basically. And it was very difficult for the programmers to actually manage their code. Later system programmers did this. But now hardware and hardware-software cooperatively manages memory. If physical memory is not enough, automatically the system, hardware and software together, bring in blocks from disk and actually demand page out some of the blocks such that the blocks that you need keep in memory. Addressing modes, we've discussed this. Unaligned memory access. Again, if you have more addressing modes, it's good for the programmer actually in general, but it's hard for the microarchitect. Unaligned memory access, if you support unaligned memory access, this is good for the programmer again. It's harder for the microarchitect. Does that make sense? Because if you do not have unaligned memory access, the compiler or programmer needs to align the data. Let's take a look at alignment. How many of you know alignment? Have you studied it? How many of you don't know alignment? That's okay. You can say. Some of you. So alignment means basically, it depends on what kind of, how big of a data you're accessing. But 4-byte word alignment means that all of the words that you're trying to access needs to be aligned at 4-byte boundaries. That's it, basically. It's a very simple concept. For example, this is the 4-byte boundary. This is, you have bytes 0 through 3 over here, bytes 4 through 7 over here. You can think of this as alignment in memory. If you're trying to access byte 3, 4, 5, 6, these are not aligned, right? Because this is actually not starting at a word-aligned address. There's a really easy way to check alignment, right? If you are, and this involves modulo calculus. Let's say you're checking whether an address is n-byte aligned. Let's say address A. Is address A n-byte aligned? What you need to do is A modulo n, you're basically testing if this is equal to 0. Right? If it's not, then it's not aligned. If it is, then it's aligned. Right? Basically, if n is 4, if it's 4 byte aligned, your addresses, the aligned addresses are 0, 4, 8, 12, 16, dot, dot, dot. That's it. And if you're accessing any other address, let's say you want to access address 3, just like we do over there, then the question is, does the processor support this, or does it not support it? In case of MIPS, if you have these 2 instructions, then the answer is no. The processor doesn't support this alignment. The processor says, I cannot complete this memory access, right? Because it's not aligned. And that's the idea of alignment. The programmer needs to align the data such that this works fine, right? Which means that if you do not support this alignment, it's harder for the programmer to do things. Now, a lot of the, actually, I think alpha, well, ARM is a little bit better than MIPS. Do you know how alignment works in ARM? Yes, some of you do. It's not perfect. It's not like x86 as I'll show you. In x86, there is no alignment restriction. x86 says you can give me any address that's byte aligned, as long as it's byte aligned. Well, it's a byte addressable ISA, so everything is byte aligned. I'll give you the data you want. Right? With your load instruction, you can give me any address and I'll give you the data. This is nice, right? The programmer doesn't need to do anything about the alignment of data. This is so the reason why this exists is because of hardware restrictions. Basically, if you do an unaligned access like this, then the hardware needs to have enough shifters and rotators such that. So this is the word you're trying to access, right? Byte 3, 4, 5, 6. To be able to do this, the hardware needs to be able to load all of this into a register. The hardware needs to take these 3 bytes, put them to the top, and this 1 byte, and put them to the bottom, right? So you need to have the shifting and rotating logic to ensure that this happens. Now, this was costly in the old days. It's still costly, relatively, right, in relative terms. That's why if you do not have this alignment support, you do not have this rotating and shifting. And also, you may need to access multiple memory locations, right? If the hardware, if the memory looks like this, if 4 bytes are here and the other 4 bytes are here, you may need to access this location first and then this location next to get an unaligned word like this. That's one of the other reasons earlier machines did not really support this alignment. Or machines that chose not to support alignment did not support alignment, because you may need 2 memory accesses, which may or may not be true depending on where the bytes are located. We'll talk about memory later on. There may be many, many choices as to where the bytes are located. But assume that these 4 bytes are located in one memory location and these 4 bytes are located in another memory location, then you need 2 memory accesses, right? Which means that a load instruction now needs to be translated into 2 memory accesses in hardware if you're supporting unaligned accesses, which is more complex. And also you need to do this rotation to ensure that the right bytes end up in the right place in the registers. That's why unaligned access is more complicated in hardware. But even MIPS, simple RISC ISAs, provide separate opcodes to help alignment. They still do not do alignment easily, but they help alignment. Basically, they have these opcodes, which I'm not going to go into in detail, but load word lower and load word, I think left or right. Left or right, right? Different ISAs have lower or upper also, but this is left or right, because this is not U. Load word lower and load word right. Load word left and load word right. Basically, what it does is you provide an address. First, you provide an address that starts at byte 6 over here, and it's unaligned. Now, it's not aligned at the boundary of 4 bytes, right? But if you use load word left, it's OK. What it does is it takes these bytes and puts them to the left of the register. 3 bytes to the left, right? And then you do a load word right, another load, to this location to get byte 3. And once you do load word right, you get only 1 byte. and that goes to the right. And that's how you can achieve alignment in software using these two instructions that are unaligned. In x86, you don't need to do this. In x86, you say, load from byte 3 for me a word, and you get this one magically. That's the beauty of having unaligned access supported by your instruction set architecture and hardware. Make sense? Oh, I don't know what happened. I guess I ran out of battery. Oh, okay, recharged a little bit. Okay, x86, load and store instructions automatically align data that spans a word boundary. Basically, programmer and compiler does not need to worry about where the data is stored. So if you look at this, I'm not going to read this again, but basically it says you do not need to align anything. However, to improve the performance of programs, data structures, especially stacks, should be aligned on natural boundaries whenever possible. And they also say the reason. This is the beauty about reading architecture manuals. The reason for this is that the processor requires 2 memory accesses to make an unaligned memory access. Aligned accesses require only 1 memory access. That turns out this is actually not always true, but to discourage programmers from using this, it's a good idea. To basically, they say that you want to align your data, right? So alignment, maybe the performance is a totally different issue. You may support unaligned accesses, but it may still take a long time to get the 2 words, right? Okay, and this is one example of unaligned access in x86. These are all the operations that are supported, basically. And this is a nice example, basically. You can do a byte. You can do word unaligned accesses, word aligned accesses, double quad word unaligned accesses, double word unaligned accesses. And ARM is actually kind of in the middle, but I'll let you figure that out for the sake of time. So there are pros of having no restrictions on alignment and cons of having no restrictions on alignment. And I think I've covered all of this, but I'll let you do this exercise. I don't have it on the slides. It's again a programmer microarchitect trade-off, right? Who gets to do more work? And I guess to think about the performance and energy as well, right? If you want to do an unaligned access on a processor that doesn't support unaligned access naturally, that takes more instructions, right? So that's your code size increases also. Okay, any questions? I've covered a lot of ISA level trade-offs. Are these interesting? These exciting? Yeah, that's good. So you may. It's good to think about designing future ISAs as well. We've covered very little space actually. There are other ISA level trade-offs, for example. Well, we're going to cover them later when we get to it because you don't have the background yet. But when we talk about multiprocessors, for example, do you expose some of the semantics? Do you have some support for synchronization in the ISA that's exposed to the programmer, right? Lock instructions, for example, in x86, atomic operations in x86 enable synchronization better. Barrier synchronization, actually we covered barrier synchronization, right, in data flow. As far as I know, there is no such instruction in x86, but there are instructions that can support it. There are instructions that can support locking, like compare and exchange instructions in x86 that can support locking. Do you support these or do you not support these? Well, if you support them, programmer's life becomes a lot easier. Okay, I guess let's see, we still have time. That's good. Let's talk about microarchitecture a little bit. We're going to cover microarchitecture in the next few lectures. And this is about implementing the ISA, right? And several questions I'll ask. Basically, how does a machine process instructions? That's what microarchitecture is all about. I guess the first question is, what does processing an instruction even mean, right? Remember the von Neumann model. Von Neumann model clearly defines what does processing an instruction mean. Basically, it defines an architectural state before an instruction is processed. Architectural state means programmer visible state. Again, anything that's architectural is visible to the programmer. You process an instruction, and you generate another architectural state, A prime, let's say. This is the programmer visible state after an instruction is processed. And processing an instruction is whatever happens in between to get from A to A prime. Of course, whatever happens needs to specify need to obey one specification, which is the ISA specification of the instruction, right? That's the only thing that you definitely need to obey when you're exposing this A prime to the programmer. So A prime needs to be consistent with the ISA specification. But in the middle, you can do many, many different things. And that's the beauty of microarchitecture. How can you do many, many different things over here to get better performance, better energy efficiency, maybe simpler design, faster design, better reliability, ... right? Okay. Basically, ISA specifies abstractly what A prime should be given an instruction and an initial architectural state. It defines an abstract finite state machine. You all know finite state machines, right? Yes, good. That's what 240 was all about. Basically, state, in this finite state machine, I'm going to call the programmer visible state as a state, and next state logic as the instruction execution specification. Right? Next state logic implements that specification. And from the ISA point of view, there are no intermediate states between A and A prime during the instruction execution. Right? No intermediate states. That's the programmer's point of view. One state transition per instruction. But microarchitecture is totally different, could be totally different. It implements how A is transformed to A prime. And there are many choices in this implementation. Basically, you can have programmer invisible state or intermediate states to optimize the speed of instruction execution. For example, you can do multiple state transitions per instruction, right? You could do multiple instructions in parallel. One choice could be this. You actually implement exactly what the ISA says in a single clock cycle. Transform A to A prime in a single clock cycle. Another choice could be this. You start with the architectural state, you add to it some, and then in the next clock cycle you go to the same architectural state plus some microarchitectural state. In the next clock cycle you can go to the same architectural state but some other microarchitectural state. Next clock cycle, the same architectural state but some other microarchitectural state. And then next clock cycle you go to the ISA specified architectural state. You can take multiple clock cycles to transform A to A prime. This is the difference between single cycle versus multi-cycle microarchitectures, and many other microarchitectures fit in this definition choice too. So the very basic instruction processing engine, it looks actually like this. So we'll cover choice 1 a little bit, and we'll see its downsides. And I'll try to cover it fast, because it's a really old idea. But it's important to understand the fundamentals and the downsides of this. Each instruction takes a single clock cycle to execute. And you have only combinational logic. Well, to ensure that this happens, you need to have only combinational logic to implement instruction execution, right? Basically, you have no intermediate programmable invisible state updates. This is it. Basically, a single cycle machine looks like this, and this is what you're going to be building soon. We basically have some state and some combinational logic that generates A next, or A prime. I guess to be consistent, I should have said A prime over here, right? Since you've taken 240, you can tell me what is the clock cycle time determined by in this case? That's right. Basically, once the critical path, the longest latency in the combinational logic, right? That's right. So what is that critical path or longest latency determined by in this case? Yes? Say it again?
Well, not the complexity of instructions stealing, how many instructions it has to deal with and how complex they are.
That's right. Basically, I think what you're getting at is, because we're processing one instruction, remember, A to A prime is generated after processing one instruction when A is the input. So the instruction that takes the longest determines this critical path, right? Because this combination logic actually implements many possible instructions, but at any point you're executing one instruction. So basically, the critical path is now determined by the instruction that takes the longest to execute. Keep that in mind. We'll get to it. But let's remember what programmable visible architectural state is. This is A. A basically looks like this. It's memory, program counter, and registers. Right? You've seen this before. So in single cycle machines, each instruction takes a single clock cycle. All state updates made at the end of the instruction's execution. The biggest disadvantage is this. The slowest instruction determines the cycle time. And as a result, you get a long clock cycle time. think about instructions. You have an add, which could potentially be done quickly, and you have a memory access, or divide, let's say. Memory access is a little bit difficult to think about in a single cycle machine because your memory needs to be combinational, right? When we talk about single cycle machines, we usually think about operand instructions. Those operate in single cycle. So let me restrict myself to operand instructions. You have an add that takes some nanoseconds, and you have a divide. We want the clock cycle to be determined by the divide? Probably not a good idea, right? But if in a single cycle machine, you have no choice because you wanted to implement everything in a single cycle. Every instruction's execution in a single cycle, which means that the longest instruction determines your clock cycle time. Multi-cycle machines are therefore more advantageous in they're more complex too. Instruction processing is broken into multiple cycles or stages, and state updates can be made during an instruction execution, except they're not architectural state updates. Right? They're not visible to the programmer. Well, I've already said that. The advantage is now it's not the slowest instruction that determines the cycle time, but it's the slowest stage. Right? It's the slowest stage that determines your cycle time. And if your stages actually are nicely balanced, hopefully you have a good cycle time. Right? Does that make sense? Yes. So both single cycle and multi-cycle machines literally follow the von Neumann model at the microarchitecture level. Keep this in mind also. We're going to change that. So while I've talked about instruction processing broken into multiple cycles or stages, let's talk about the life of an instruction, basically. What is an instruction processing? How does the instruction processing happen? I'll call this cycle also, but unfortunately this is overloaded with the other clock cycle. But this is the cycle of life of an instruction, if you will. Instructions are processed under the direction of a control logic, step by step. And these are a sequence of steps to process an instruction. That's what an instruction cycle is. There are really 6 phases. These are defined by the Patton and Patel book in chapter 4. And these are probably the most comprehensive 6 phases. You need to fetch an instruction. You need to decode it. You need to evaluate the address for the operands. You need to fetch the operands once you have the address. You need to execute, and you need to store the result. Right? Now, actually, not all instructions require all of these stages. But there are some instructions that may require all of these stages. But in a single cycle machine, all of the 6 phases of the instruction processing cycles, all of this, takes a single machine clock cycle to complete. Not a good idea, right? Because some instructions may require all of these stages, some of them may not, right? Keep that in mind. And some of them may take execute, right? Execute may take a long time for one instruction versus a short time for another instruction. Divide versus add. Think about that. In a multi-cycle machine, all 6 phases of the instruction processing cycle can take multiple machine clock cycles to complete. So each of them can take multiple cycles, actually. In fact, each phase can. I actually said that over here. Does that make sense? OK. I think these are simple concepts, so I'm going to go over this quickly. But think about the design of instruction processing in another way. Again, we're transforming data to data prime, or architectural state. I changed this to AS here, to AS prime. This transformation is done by the functional units that operate on the data. And these units need to be told what to do with the data, right? You have some input data, which is the input architectural state. And you have these units that need to do something to that input data such that the architectural state prime is generated. To be able to do this, an instruction processing engine actually consists of 2 components. And you're going to design both components in your labs. One we call the data path. This consists of the hardware elements that deal with and transform data signals. Right? This is really how the data moves. And the other is, well, I don't have it. Let me actually do this. The other is the control logic. And control logic specifies what happens to the data, right, as it moves around. So the data path actually consists of 3 things. One is the functional units that operate on the data. There's an adder, for example. Hardware structures that actually facilitate the movement of the data, that enable the flow of the data to appropriate places, appropriate functional units and registers. These are, for example, wires and muxes. You need to have that, and you're going to use that in your designs. And also, finally, the storage units that store the data, registers, for example. These are all data path elements. Control logic, on the other hand, consists of all the hardware elements that determine the control signals. Signals that specify what the data path elements should do to the data. What should the ALU, for example, do to its inputs? Should it add them? Should it multiply them? Should it divide them? Should it subtract them? That's a control signal, right? And control logic determines what that control signal should be set to for this particular instruction that's being processed at this time. Similarly to the muxes, right? Which input should this mux pass to its output, right? That's determined by the control logic. And control logic determines the control signals. However those control signals are determined is dictated by the instruction that's being processed in this cycle, in a single cycle machine. Okay. So control versus data, control and data in a single cycle versus multi-cycle machine. In a single cycle machine, you necessarily need to generate the control signals in the same clock cycle as data signals are operated on, right? Because you have one long clock cycle. And everything related to an instruction happens in one clock cycle, which means that your clock cycle needs to be even longer than we previously thought maybe, right? Because you first need to generate the control signals, they need to stabilize, and after that your data path elements needs to stabilize and move the data, right? It's actually not a good design. Usually, if you're designing a system, it's better to overlap control and data such that they happen in parallel rather than in serially. Otherwise, you have long processing times. If your control needs to happen, right? If you wait for your data path processing to happen until your control happens, then it takes too long. If you kind of overlap them, if you generate your control signals for the next cycle in this cycle, then you're kind of overlapping processing, control and data processing. We'll see this in a multi-cycle machine. Basically, in the multi-cycle machine, control signals needed in the next cycle can be generated in the previous cycle, right? At least most of them. Maybe not all of them, but most of them. If you know what phase of the instruction you're processing next, you could do this. And this is the actually nice thing about pipelining also. You can basically generate the control signals that you need in the next stage in the previous stage. If you don't know about pipelining, keep this in mind. Basically, you're generating control signals early on. And the upside is latency of control processing can be overlapped with latency of data path operation. And we'll see this difference clearly in microprogram multi-cycle microarchitectures. So there are many ways of designing the data path and control signals, and you'll do that in your lab. Well, actually, you'll do a lot of these. And you'll have a homework question where you'll do a single bus versus multi-bus data paths. You may have exam questions on this too, actually. You could have micro-coded microprogram control, which we'll talk about, or hardwired combinational control. Oh, this was hardware combinational control, right? Whereas I had this microcode ROM that translated repeat MOVS into smaller instructions. That's a micro-coded control. So these are two different styles of control. Well, I guess I've already told you about this. In that case, it wasn't the control signals stored in the memory structure, right? It was really the instructions. But I didn't tell you the full picture because in x86, they partially store the control signals in that structure. They don't really store the instructions and redecode them. What they do is they really store the control signals such that they don't need to redecode all of those individual instructions. So it's really a microcode ROM. That's why it's called a microcode ROM in that case. But we'll get back to the microprogrammed microarchitecture soon. Well, obviously, since control signals dictate what happens on the data path, the signals themselves and the structure depend on the data path design, right? If you do not have an ALU, you don't need to have a control signal for an ALU, obviously. And if you have a mux, you'd better have a control signal for that mux, unless you don't care, unless the outputs don't care. Unless you're generating a random number, maybe, right? That could be useful. But even then, you may need to randomly control something. I don't know what that means. That's what cold weather and sickness do to you. I mean, I guess we could go into an aside on random number generation, but we don't have a lot of time. That could be some food for thought for those of you who are interested in architecture. Like, how do you generate true random numbers in hardware? That's a tough thing to do. Okay, let's do performance analysis a little bit, and then I'll be done. Basically, this is my last slide. You can think of the execution time of an instruction as the cycles it takes to execute the instruction times the clock cycle time. Right? Have you guys seen this equation before? No? Basically, CPI is number of cycles to execute, or it takes to execute the instruction. And cycle time is clock cycle time, basically. How long is your clock cycle? For a 1 gigahertz machine, it's 1 nanosecond, right? At least I can calculate this in this state. That's good. Execution time of a program basically is the sum of, for all instructions that are executed, sum of that values, right? You may be executing 1 billion instructions, and for each instruction you have a different CPI, but the clock cycle time is the same. That's basically the execution time of the program. Right? Now, to make performance analysis a little bit easier when making trade-offs, we break this equation like this. This is called the iron performance law of computer architecture, if you will. This is execution time. Number of instructions times average cycles per instruction times clock cycle time. Now, as a microarchitect, your goal, or as an architect, your goal is to minimize execution time. Assume that performance is your only goal. You could actually minimize execution time by minimizing the number of instructions, minimizing the average cycles it takes to execute the instruction, and the clock cycle time, right? Minimizing the clock cycle time. So you have 3 degrees of freedom, if you will. Assuming the program is constant, it's given to you, you're not allowed to change the number of instructions, then you have 2 degrees of freedom. Right? We're going to get back to this equation later on, but think about single-cycle microarchitecture performance versus multi-cycle microarchitecture performance. In a single-cycle microarchitecture, CPI is by definition 1, right? Every instruction takes a single cycle. But clock cycle time is long because of that reason. So these are actually related. CPI and clock cycle time is related. Depends on how you divide the instruction processing. Right? If you say, I'm going to take a single cycle to execute all instructions, basically execute any instruction, then you by definition made your clock cycle time long. Unless your instructions are such that they're all very balanced, right? Which is very difficult to achieve. On the other hand, multi-cycle microarchitecture performance, CPI is different for each instruction, right? Cycles per instruction is different. It takes, let's say, 1 cycle to execute an add versus 50 cycles to execute a divide. Now you made those independent, these 2 different instructions independent. As a result of this, clock cycle time is short. You've determined your clock cycle time in some other way. You can now minimize this one, right? It's independent of the execution of an instruction. It's independent of the instruction processing cycle. And the hope is that average CPI is hopefully small. Let's say most of your instructions are adds. Hopefully your cycles per instruction is small, right? So the upside of this is you have 2 degrees of freedom to optimize independently, right? That's the big upside of a multi-cycle microarchitecture. In a single-cycle microarchitecture, you don't have degrees of freedom. Actually, you've set CPI to be 1. The only degree of freedom you have is clock cycle time, right? You can optimize that logic, that combination logic, that next site logic, as much as possible to minimize the clock cycle time. But then you have limited options because you're really bound by that long instruction, right? Now the option is basically how fast you can make that longest instruction go. And then later, how fast you can make the next longest instruction, which becomes the longest instruction after that go. It's tough to do this. Whereas here, these are independent now. You could optimize CPI for different instructions, and you can also optimize clock cycle time totally independently. This is not dependent on the instruction now. So that's the upside of multi-cycle microarchitectures. So I guess I'll part you with this one, but give this some thought, because this is the enabler of a lot of microarchitectural trade-offs, and you can optimize all of them. But there may be trade-offs. If you increase clock cycle time, you may need to reduce CPI, for example, and vice versa. Okay, I'll see you Friday.